Hello everyone, this is Hsuan-Hao from Taiwan. I'm a recent graduate from Purdue University, and I was working in the ultraviscous optics and optical fiber communication lab from 2016 to the end of 2020. Since this January, I returned to Taiwan to fulfill my substitute military service obligation in my hometown. And I will continue my research, hopefully, after I complete the service by March 2022. I thought it would be a good opportunity to record this as a future reference and also for anyone who's interested in my research. So today I will talk about the work I've done during my PhD and mostly during the collaboration project with Arbitrary National Lab. The title is Quantum Information Processing with Frequency Band Qudits. This is the outline of my talk today. I will start with a brief intro of frequency domain quantum information processing, and then start to discuss some of my main PhD works about this device called quantum frequency processor. Then I will have 2 to 3 slides covering a little bit about the work outside the scope. Finally, I will have my conclusion and outlook section, sharing some of my thoughts on using such degree of freedoms for quantum information processing. Now let's start with the first sections. Across all the possible degree of freedoms one can encode information in single photons, we're mainly focused on the frequency domain. So what's the motivation of exploring this degree of freedoms compared to other well-developed photonic degrees of freedom such as time, path, polarization, and OAM? So for most people, frequency is naturally used as the carrier of quantum informations. For example, one could have 2 atomic systems, each of them entangled with an emitted photons in polarizations, and they apply quantum frequency conversions to the optical C-band for single-mode fiber transmissions. At the middle station, they perform entanglement swapping. In this case, such frequency conversion has to make sure both photons are identical in frequency, at the same time preserve their original quantum informations. Another application is to utilize frequency as a resource for assisting other degree of freedoms, such as, in this case, a wavelength multiplex quantum network based on polarization qubits. They utilize the hyperentanglements in the system to distribute photons to multiple users at the same time. A recent set of experiments I was luckily involved, where we use wavelength selected switch to distribute such state in a flexible bandwidth allocation fashion. And we later upgraded into a 3-node quantum local area network in the ORNL campus. For us, we're more interested in using frequency itself as the encoded informations. The discovery of chip-scale quantum frequency comb allows one to generate extremely high-dimensional 2-photon state from a single device. Moreover, utilizing this device we have been researching on in the past few years, called quantum frequency processor, we could perform parallel control of single photons or even 2-photon state in a single processor. The scheme is extremely stable since everything happens in the single fiber optic spatial mode. Also, the control adjusts externally applied voltage, which does not add any extra noise to the system. We believe this could be an attractive way to encode information, especially for networking applications. So is frequency encoding ready for real-world applications? I'm going to use this example from a recent Nature Photonics paper and try to connect to our own findings. This is a conceptual figures illustrating quantum teleportation on a chip. The chip was designed for path-encoded photons. Other than that, there is also single photon sources and also quantum memory on the chip. For now, that just focused on the processing side. For teleportations, we have a qubit here to teleport. Let's call it qubit A. We need to prepare a maximally entangled state and send one of the photons with qubit A for Bell state measurement, while the other photon is stored in the quantum memory and waiting for the measurement results. Once the measurement is done, ask the quantum memory to release the photons, then we rotate it based on the measurement results. Now the final qubits will have the same state as the qubit A. This is called quantum teleportations. Let's take a deeper look and see if we have the functionality required. For preparing the entangled state, this example using Hadamard plus CNOT to entangle 2 separate qubits. And yes, we did demonstrate the frequency version of this in some of our ORNL Purdue collaboration projects together. Bell state analyzer recently developed this, and this paper is now under review in Optica. Arbitrary rotations was investigated and implemented as well last year. What makes frequency domain more attractive is its capability of scaling to higher dimensions. If we consider a higher dimensional version of quantum teleportation, then first of all, the entanglement source has to be a two-qubit state instead of a two-qubit. So we might need to perform a high-dimensional quantum state tomography to make sure the initial state has extremely high state fidelity. We recently developed a method utilizing randomized measurement to characterize the highest dimension to date for frequency entangled photons. Now the paper is under review in Nature Photonics. What else? For arbitrary rotations, now it's Qudit rotations. We also explore some functionality and discuss how their performance scale with the required resource. I might not be able to cover all of them in this video, but if you're interested, feel free to take a look at this reference I listed here. Now let's dig deeper into some of the demonstrations using this device called quantum frequency processor. This is a concept firstly proposed by Joe Lucas and Pavel Lugovsky, a current member and a former member in the quantum information science team in ORNL. For frequency in QIP, there are 3 building blocks. First of all, we need photonic qubits. In this case, logical 0 and 1 are represented by a single photon populating omega 0 or omega 1. If we have more than 2 levels, we can then extend to high dimensional state, and we call it qudits. The D is the dimension of the systems. Usually in the lab, what we prepare is a 2-photon frequency qudit state, generated from a spontaneous Fourier mixing process in the nonlinear resonators, or a spontaneous parametric downconversion process from a nonlinear waveguide, followed by some spectral filtering in a cavity. In either case, we'll have strongly correlated photons in time and frequency. To manipulate a photonic state, usually we will need to apply phase shift to each mode. For phase shift, we use this device called pole shaper. It's based on a 4F setup where we disperse frequency components to different spatial locations on a liquid crystal modulator array, and then we apply phase shift by applying voltage across the pixels, just like a bank of phase shifters in parallel. One thing we need to be careful is that the frequency beam spacing needs to be large enough compared to the spectral resolution of the pole shaper, such that we can manipulate each mode independently. We call it line-by-line shaping. Other than phase shift, we also need to mix different modes to rotate the state. The device we use is called electro-optic phase modulators, or EOM in short. Driving EOM with a periodic waveform, we could generate frequency sidebands. The sideband has the spacing equals to the driving frequency. So if we drive it with a periodic waveform, with a frequency exactly equals to the mode spacing, then we can mix, or we can say rotate the state, that's say from 0 to 1 or 0 to 0 plus 1. This is a figure showing how a single frequency mode transform when we drive it with single sinusoidal voltage with increasing modulation depth. Probability amplitude of the sideband follow that's a function of the first kind. Special note is that this mode transformation EOM is a Toeplitz matrix. That means, for example, take a look at this figure again. If we send omega 1 instead of omega 0, we're going to see exactly same distributions, but shifted the whole spectrum 1 mode away. This suggests a single EOM cannot be a quantum gate, since if we find a waveform magically convert, let's say, frequency mode 0 to mode 1, then if we send in mode 1, it's going to hop on to mode 2. That could be outside of the computational space we're interested in. Instead, we found out that using concatenations of EOMs and pole shapers, we can build a lot of quantum gates for frequency. The way we model it is using metric formalisms. For example, pole shapers can be represented with a diagonal matrix. The diagonal elements are spectral phases we would like to apply onto the different frequency modes. For EOM, we also use the diagonal matrix to represent the transformations, but now the diagonal elements are discrete samples of the temporal phases. But since we work with frequency, we're simply using Fourier transform to keep changing between time and frequency bases. Note that these matrices has dimension larger than the quantum state we're interested in. The reason is pretty obvious from this cartoon. When the input mode is going through this EOM, we're actually having newly generated frequency sideband spread outside of this computational space, in this case represented by this dash box. After proper phase imposed by the pole shapers in the second UM, they can return to this dash box due to proper spectral interference. So the design of QFP comes down to these question marks. What modulation waveform for EOMs and pole shapers we need to realize specific quantum operations? To solve this problem, we rely on two metrics commonly used in the community. The first one is success, that describes the probability of photons staying in a computational space. Second one is fidelity, that describes the purity of the operations. Take a look at this cartoon for example. This is a Hadamard operations, also known as the Beamsplitter. For success probability, only cares about how probable the two photons can stay in this dash box, but not the correctness. For fidelity, only cares about how equal these two frequency modes are at the output. In the simulations, always pushing fidelity close to unity, usually larger than 0.9999 or 49, while at the same time, we want the success as high as possible. In the past year, we're searching around better cost functions to optimize these two metrics together, and we found one. Our cost functions look like this. It penalizes the optimizer more when the fidelity is far away from the target fidelity, and once it surpasses the target fidelity, then the optimizers only cares about the success. We had a lot of fun using these algorithms called particle swarm optimization, or PSO in short. This is a meta-heuristic algorithm trying to mimic how a swarm of bees or birds trying to find the food. Each of the particle here, this blue dot, is a vector, representing a possible solution for a QFP. They're searching around the solution space to find the worm, that is the target solutions. They modify their moving direction and behavior based on their own history, as well as the history of other particles around them. So it's like these flock of birds can communicate with each other, and in the algorithm setting, we could set the birds extremely egocentric or extremely obedient. There are just a lot of weighting parameters one can tune. We found this algorithm is performing better than our previous one using nonlinear constraint optimization method, especially when we're going to higher dimensions and the number of unknown parameters are getting larger and larger. This is the current versions of the quantum frequency processor looks like. Central part is a pole shaper, sandwiched by two EOMs. Pole shaper can be directly programmed by the computers, that's pretty simple. For both EOMs, we need RF oscillator to generate sinusoidal voltage, and we use a sequence of RF amplifiers, RF shifters, RF attenuators to precisely control the driving voltages. In the current version of quantum frequency processor, we can at most drive 2 RF tones due to the limited RF bandwidth of the oscillators and the EOMs. Usually we set it at 25 and 50 GHz or 20 and 40 GHz. For the test source, if we simply want to look at the gate performance, we can probe it with classical frequency comb with a few comb lines. This can be prepared with a C-level lasers modulated by an extra modulator, followed by some amplitude and phase filtering in the pole shapers. If we're testing with quantum source, in the past we're mostly using a 780 nanometers continuous wave laser pumping a Piplin waveguide, generating broadband down-converted signal either photons, followed by epsilon to carve out equally spaced frequency bands. This is an example joint spectral intensity measurement we had for our type 0 Piplin source. After such state processed by the QFP, we demultiplex the output by colors and then perform coincidence detections between different frequency bands. Now let's take a look at some of the past demonstrations. First of all, the most important element in linear optical quantum computing is the Beamsplitter. In the path encoded, it's very straightforward. It could be a bulk Beamsplitters or an on-chip directional coupler. For frequency, we utilize 3-element QFP driven by this waveform to realize high-fidelity frequency beam splitting operations. For UMs, there are simply two sine wave. They're 180-degree phase shifted with the pole shaper, program a step function of pi phase jump between these frequency modes. Here are the experimental spectra we obtained using the classical input, showing how such frequency beam splitter or Hadamard gate transform a single line input into two balanced lines at the output and vice versa. The most attractive features of the QFP are twofold. First of all, the absence of noise source. Using a attenuated laser at the input, we show excellent visibility in the spectral interference experiment using weak coherent state. Second of all, its inherent capability for parallel operations. Since we have many pole shaper pixels covering a total of 5 terahertz bandwidth on the pole shaper, if we include proper guard band between each beam splitter, we can implement approximately 33 of beam splitters in parallel. Perhaps for now, one might be hesitant about working with frequency based on these slides, since it took so much effort just to build a basic beam splitter. But later in the presentations, we will see how frequency might catch up and hopefully perform better in the scalability. The first application we look at after the frequency beam splitter is the Hungman-Dal interference. HOM is the foundational quantum effect underlying two-qubit gates in the LLQC paradigm. In conventional HOM, one mixes two photons on a 50-50 spatial beam splitter while scanning some parameters to control their overlap. We observe photon bunching at the exit ports. In 2010, Michael Raymer suggests that the same effect can be realized even with two photons of different colors, provided that one uses an active beam splitter to mix them, i.e., the beam splitter is going to erase their frequency difference. Our case, we found out by simply tuning the phase jump alpha on this pole shaper, while the other two UMs remain fixed, we can create a tunable frequency beam splitter with reflectivity gradually changing from 0 to 50% and then back to 0. Now, when we send in a pair of signal either photons with their frequency matches those of the beam splitter, we could create this Hungman-Dal dip where we gradually tune the reflectivity and transmissivity of this tunable frequency beam splitter by scanning this phase jump alpha. You obtain the visibility around 97% without accidental subtractions, well surpass any of the existing demonstrations in the frequency platform. From the last slides, we came to interesting conclusions. With the same EO modulations but different pole shaper configurations, we could realize different operations. This suggests the idea that we could program the pole shaper accordingly such that photons at different subbands could see different gates, meaning different gates in parallel. Now let's take a look at this figure again. We plotted two pairs of black arrows corresponding to frequency modes of two photons, A here and B here. With this phase jump alpha both equals to pi, we're implementing parallel Hadamard operations for both photons. When the phase jump alpha is pi for photon A, but 0 for photon B, we're realizing Hadamard operations for photon A still, but identity operations for photon B. The reason it's an identity operation is that now the pole shaper is doing nothing here. Photon B experienced two EO modulations, one after the other, with this modulation cancel out each other due to the 180-degree phase shift. Experimentally, we prepare a frequency band entangled state where idler photons occupy spin -4 and -3, while signal photons occupy spin 4 and 5. We pass both photons through the QFP, implement either identity or Hadamard gate for these two subbands. After the gate operations, we frequency demux the output photon pairs and measure their spectral correlations. Now let's take a look at the final result. When both operations are identity, spectral correlations reflects what the input state is. Their frequencies are anti-correlated as a result of energy conservations. When we apply Hadamard to one of them, we erase the correlations such that each of these outcomes in this 2x2 qubit subspace has the same probability. Now when we apply Hadamard operations to both photons, the frequency correlation changes from negative to positive correlations. With two ways to look at this. First of all, we could see this as generating different quantum states, rotating the original psi plus Bell state to phi plus Bell state. We could also see this from the QKD point of view, where results are correlated when we measure in the same basis, while for at least two cases when we measure in different bases, their outcomes are equally distributed. We could even use the result to perform entanglement witness due to the fact that these two photons are correlated in two mutually unbiased spaces. Finally, using Bayesian analysis, we can utilize these measurement results, although not complete, to perform quantum state tomography of the state. Final application related to frequency Beamsplitter I'm going to discuss here is the frequency version of Bell state analyzer. Consider we would like to entangle two distant ions. We can locally entangle them first with a photon using some internal degree of freedoms. For example, we could have spin polarization entangle. When the spin is down, the photon should be horizontal, and the spin is up, the photon is vertical. Now we use fiber to bring these two photons together at the input of the BSA. A successful BSA measurement between these two photons will project the two ions, which never interact with each other, now entangled. This is the concept of entanglement swapping for remote entanglement. However, there is a caveat. This statement only works when these two photons are identical in all other aspects. What happens when these two photons are slightly different in their colors? This could stem from some energy shift because of the local qubit environment. One of John Wei-Pan's papers investigates such an issue. They prepared two photon pairs. Both of them entangle in the polarization degree of freedoms. However, one of the photon pairs shifted 40 MHz away from the other. They sent one photon from each pair to the central Bell state analyzer to perform the entanglement swapping operation we just discussed. What happened after the final states for this capital A and capital B? Ideally, they wanted to be a Bell state, but turned out there's an extra phase term between HH and VV. Inside this internal phase term, there's delta omega. That's the 40 MHz frequency separations between the two photons. Delta T is the photon arrival time difference in the BSA. That could vary from event to event and is totally random. There are two solutions. One, of course, is to erase the frequency difference somehow, while they adopt the other solutions. They keep track of this delta T real time and feed forward to correct the phase using a pocket cell. That can make sure the final state is pure. Here they show the polarization visibility experiments for the final state A and B with and without feed-forward operations. It's pretty obvious without feed-forward, the final state is totally mixed, so the visibility is 0. This method, however, will still encounter an issue if the frequency separation is too large and we don't have the accuracy of determining delta T precise enough due to the detector jitter. Let's consider an even more general case where the ion is locally entangled with photonic frequency. The spin up and down are correlated with two different frequencies. Suppose we have second ion also has atomic state entangled with photonic frequency, but now the center frequency is shifted. And there is currently no solutions to perform Bell state measurement for this kind of state. Here we propose solutions using our device. As the proof of concept demo, we consider a simple scenario where the frequency spacing within photon A and photon B are exactly 20 GHz. The center frequency shift between A and B are twice the spacing, 40 G. If we plot them side by side on the frequency axis, we're dealing with 4 frequency modes spaced equally by 20 GHz. In order to design a frequency version of the BSA, we can borrow the idea from the past design in other degrees of freedom. We found out all we need to do is to realize 2 sets of Hadamard gates. But now instead of mixing the color in each photons, we're actually mixing the lower frequency modes between photon A and B, that is A0 and B0, and the higher frequency modes between photon A and B, that is A1 and B1. This requires 2 interleaved frequency Beamsplitter without any sort of crosstalk. Turn out from the engineering point of view, it's very straightforward to convert our single frequency Beamsplitter into 2 interleaved Beamsplitters. by simply doubling the RF frequency from single frequency mode spacing to 2-mode spacing, and reprogram the pole shaper to apply phases to 2 sets of grids, or supergrids. We can realize such operations. Send the entangled photon psi plus and psi minus, the outputs are distinct from each other. We calculate the discrimination accuracy by summing out the photon counts in these 2 bars divided by the counts in all bars. We have accuracy over 98%, showing the potential of using QFP for quantum networking applications. Okay, this is 2-qubit entangling gate, which operates on 1 qubit conditioned on the state of the other. That's a necessary component for any sort of arbitrary quantum operations for universal QIP. However, we know that photons do not like to interact with each other. In the context of LOQC paradigm, one can instead use quantum interference and pole selections to realize such operations. For CNOT gate, the maximum success probability is 1 over 9 if there is no ancillary photons. In path encoding scheme, one could break down the CNOT gate into a sequence of 50-50 beam splitters and partial beam splitters. In our scheme, instead of breaking down and synthesize these beam splitter elements by elements, we directly synthesize the whole CNOT gate by running the optimization program to find suitable waveforms for UAMs and pole shapers. The bottom right corner is the conceptual illustration showing the frequency band interference when the input state is at state 1-1. The UAMs in the setup serving as multiple interferometers, the pole shapers, when put on the right phases, can help suppress the unwanted result, for example 1-1, at the output. So here I just want to quickly go over the results. To test our CNOT gates, we prepare all 4 inputs from the 2-qubit computational basis, obtain this characteristic bit flip when the control photon is in state 1. Ideally, we would like to show this gate is truly entangling by preparing a control state in superposition of 0 and 1. But at the time, we were limited by the equipment, so we developed a Bayesian model to help us extract both the amplitude and the phase of this 2-qubit gate, even with measurements in the computational basis alone. We obtained a gate fidelity of 91%. That's not perfect, but still, this is the only 2-photon gate demonstrated for frequency encoding in any sort of platform. The strength of the QFP is its capability of manipulating multiple frequencies at the same time. So naturally, we're interested in how the performance and resources requirement scales to higher dimensions. The first example we had a deeper look at was the extension of the Hadamard gate to 3 dimensions. This is called 3-dimensional discrete Fourier transform gate, or a frequency Tritter. For path encoding, one needs to break it down into several 2x2 beam splitters and phase shifters, or a specialized design using femtosecond laser reading waveguide. Without using the exactly same setup, we simply increase the complexity of the driving voltage by adding an extra RF tone. We could realize high fidelity frequency Tritter. Here you can see an example of classical input and output transformation spectra. We probe in 2 frequency lines at 2 different subbands, where we program 2 frequency Tritter in parallel. The outputs are 3 balanced frequency lines in each subband. We could also extend what we have done with 2-qubit entangled state to 2-qubit entangled state. Assume we start with maximally entangled qubits with signal either each occupies 3 frequency bands. After we apply 2 parallel frequency Tritter, we could again flip in the correlations depending on the initial phase setting at the input. What if we go extremely high dimensions such as 10? Currently, one of the largest dimensions demonstrated in path encoding is Jeremy O'Brien's group in Bristol, in which they have put hundreds of Mach-Zehnder interferometers on a single chip to manipulate the entangled photons with dimension of 15 in each photon. In our case, we found a recipe and figured out we can still use the same setup, but now the RF signal consisting of D-1 tones for building this high-dimensional DFT gate. Here is a simulation showing a single frequency mode can be split into 10 balanced frequency modes at the output. Of course, for now, we're only focused on this specific operations, But this could be useful for a high-dimensional quantum key distribution experiment where Alex and Bob share maximally entangled qubits. They can use these operations to measure in the logical or Fourier basis. In the previous slides, you might notice that we were mostly talking about Hadamard gates or its extension to higher dimensions. But quantum networking applications such as dense coding or teleportations, one needs to apply a quantum gate like X or Y gate, that is flipping the logical state between 0 and 1. For other degrees of freedoms, any arbitrary unitary operations is usually decomposed into a few basic elements. For example, in polarizations, usually they use quarter wave plates and half wave plates. Path encoding, it can break down into beamsplitters and phase shifters. But as we just discussed, this is not the route we're going to do. Instead, we focus on numerical optimizations to help us establish the resource guideline. We use the famous decomposition method in quantum mechanics, which is 2 Z rotations and 1 X rotations. This can bring input state to any point on the Bloch sphere. Develop a theory and find out that the gate performance and the resource requirements only depends on the metrics in the middle. In this case, we can focus on the single variable theta in the simulations, assume 0 for the other 2 variables. Other rotations can be simply reconfigured by shifting the EO modulations and correcting the phases on the pole shaper. We won't cover that in the video, but if you're interested, take a look at our paper. We run the simulation and constrain fidelity to 4 nines, maximize the success probability at the same time. Here we plot the gate success with different theta and 3 different configurations. We immediately notice a strong dependence. It seems that larger the theta, the worse the gate success. Also, we can improve the gate's performance if we introduce more resources to the system, either adding an extra RF tones or an extra EOMs and pole shaper. That is quite understandable. Here I also show an example of mode transformation spectra for theta equals to pi over 2. This is the Hadamard gate. For the first configurations, we can see a small bump here. That's because of 97% gate success probability. But we couldn't see that in the next 2 configurations because the gate success is almost 100%. This is even more obvious. For theta equals to pi, we're getting a poly X gate, which can flip the frequency mode from 0 to 1 and 1 to 0. In the first configurations, the success is 78%, so we're seeing a lot of small bumps outside of this dash box. We see an immediate improvement in the second configurations, roughly 95%, eventually almost 100% in the final configurations. To show its potential in manipulating quantum states, here we use a single frequency laser but heavily attenuated down to single photon level to mimic the quantum state 0. We then apply different quantum gates to take the state from North Pole to different points on the Bloch sphere. After the gate operations, we perform quantum state tomography to characterize the output state. If the gate operation and measurements are perfect, output state should be exactly at the point where expected. On the Bloch sphere, we are seeing a few groups of dots. Each group represents the quantum gates we implement, and there are a total of 41 gates. If we look closer, there are blue circles. These are plotted at the location of the ideal output state. Ideal meaning that suppose we apply the ideal gate operations to the ideal input state. The green dots are 1024 Bayesian sample retrieved from the quantum state tomography, and we can see them surrounding the blue circle, which suggests the gate operation as well as the measurements are pretty close to the ideal. This concludes the section of QFP. Each of the applications I presented here hopefully can be very useful for some quantum networking protocol based on frequency-band qubits or even frequency-band Qudits. Now let's shift gear to talk about some of the work outside the scope of the QFP. This is the overview of some of the works not directly related to the device, but mostly have something to do with the pole shaper and EOM technology. The first one is the one utilized pole shaper as the wavelength selected switch to distribute hyperentanglement source in polarization frequency to connect multiple users at the same time. This was firstly done as a tabletop demo in Purdue with only 2 pairs of detectors in the same lab, and then we later extend to 3 buildings across the ORNL campus. Using wavelength selected switch, we perform flexible entanglement distributions by allocating proper bandwidth of the entangled photons to different users. In this demo, we not only show the possibility of equalizing the qubits shared among 3 users, but also demonstrate a remote state preparation protocol. Next one was performed in ORNL. This is to reconstruct the frequency correlations of frequency bands entangled state. In the past, people relied on raster scan to collect the coincidence between one frequency band and the other. That could take a huge amount of time to scan through the whole spectrum. Instead, we use pulse shaper to apply a set of codes. Each code is a spectral filter, and then collect coincidence by 2 bucket detectors. We then use techniques such as compressive sensing and Bayesian to efficiently reconstruct the 2 photon spectral correlations. Finally, we're exploring this recently in Purdue, where we use frequency entangled photons to sense optical delay in non-local configurations. And time resolution is not limited by the detector jitter. The idea is that the optical delay can be seen as spectral phases encoded onto the entangled photons, and different phases will contribute differently during the spectral interference at the outputs, where we use EOMs to apply frequency mixing. I won't be able to go into details, but I encourage everyone to check the reference we listed here. Instead, I would specifically like to share this work as high-dimensional frequency quantum state tomography. As we mentioned in the very beginning, the reason we're interested in frequency is its intrinsic high dimensionality. Pumping a single waveguide or a single resonator, one can generate many correlated frequency modes, and the first measurement we always did was the joint spectral intensity measurement, where we frequency demux signal either and measure the coincidence counts between different mode pairs. This is an example of such measurement showing 4 anti-correlated signal either modes due to energy conservations in the nonlinear process. However, such measurement does not provide any phase informations. Even we can measure tens of frequency modes easily in the lab, that doesn't mean we can confirm the presence of the high-dimensional entanglement, which relies on the phase coherence across different beam pairs. Usually we just assume in the ideal case that should be a entangled state. However, simply from the JSI measurement, one can question that this state, although in the best scenario, is a truly high-dimensional entangled state, but the worst scenario, it could also be a classically correlated state, meaning there is no phase coherence across these beam pairs at all. This is our proposed scheme to efficiently characterize the state. Given the input state, a total of d frequency beam pairs, here this example is d equals to 4, we use pulse shaper to apply a random set of spectral phases followed by an EOM. EOM is simply driven by a single sine wave with the modulation depth randomly selected from a specific interval. Here the range of the interval we pick is between 0, so that's no modulation, to d divided by 2 radian. In a recent manuscript submitted to Nature Photonics, one of our colleagues helped us develop a theoretical model describing why this amount of modulation might be enough. The bottom line is we need to pick an amplitude that can give us enough mixing between the frequency bands. After these 2 random modulations, repeat the JSI measurement, and because of the newly generated sideband, the JSI will no longer remain diagonal. This is an example of strong modulations with 2 radians. Each frequency mode will generate 2 sidebands at this modulation depth, and thus now you can see the signal either frequency are no longer anti-correlated. We repeat these procedures for a couple of different random modulations, and finally we use Bayesian again to incorporate the experimental data we gather and into the quantum measurement model and help us find which states can possibly contribute to the results we're seeing. The idea is this: for different input states in the presence of same modulation patterns, they exhibit different frequency correlations at the outputs. Here we quickly summarize our result. We tested this method with a frequency band entangled Qudit state generated from silicon nitride microrings. And using Bayesian method, we can reconstruct the full density matrix from a 2-qubit state all the way to 2-qubit state with d equals to 8. We plotted fidelity and log negativity. They lie comfortably within this shady area. This area corresponds to the white noise model we assume in theory. This is the highest dimension to date for any experimental demonstrations for discrete frequency bands in any platform. Now let's move on to the conclusion and outlook sections. So far, we have developed a set of tools to experimentally manipulate photons encoded in frequencies. We demonstrated some foundational experiments over the years for the frequency QIP community, include the first electro-optic frequency Beamsplitter, the first Tritter, the first Bilstein analyzer, and the first full single-qubit rotations and tomography for frequency qubits. So we come back to the questions proposed earlier. Do we have the confidence of saying frequency degree of freedoms is ready for real-world applications? Looking forward, there is still a lot of things can be looked into. One of the major goals our group is looking is to fabricate our quantum frequency processor on a single chip that could ideally cut down the loss while increasing the circuit complexity. It will also be interesting to look at other manipulation methods, both existing experimental demo or just recently proposed with theory. For example, using Chi3 and Chi2 nonlinearity, they were some of the earliest demo for manipulating the colors of photons. They have limited functionality, mostly focused on nonlinear frequency conversion or frequency Beamsplitter. However, one of their strengths is the capability of bridging frequency that are hundreds of gigahertz, even terahertz away. So maybe we could envision a future system using nonlinearity for interband conversion and our QFP for more intricate in-band conversion and control operations. There are more recent demos using high-Q microring resonators with EO modulations applied to the cavity. Marco Loncar's group in Harvard and Willis Pavlovich group in Boston University demonstrated frequency Beamsplitter using dual ring structure, which is called photonic molecule, with some theoretical discussion scaling up to higher dimensional systems with more ring introduced. Another theoretical proposal from Hsuan-Hao Fang's group in Stanford shows high fidelity, high dimensional frequency translations. The number of rings and number of RF tones also scale sort of linearly with the dimension of the operations. It'll be interesting to explore and compare which system has the best compatibility with photonic integrated circuits, or even consider a hybrid version of them. On the source side, there are more alternatives coming up nowadays. Take this one as an example. A Japanese group recently demonstrated frequency band entangled sources by coating both end faces of a type 0 Piplin waveguide to form a cavity. This could circumvent the loss in the conventional scheme, where the cavity was usually placed after the broadband down conversion process. They even modified the setup into a Sanya interferometer such that this optical source can emit photon pairs hyper-entangled in both polarization and frequency. One could also take frequency as a multiplexing resource to enhance the success rate of quantum repeaters. These will require multi-mode quantum memories to store photons of different colors, as well as reconfigurable frequency shifters or frequency Beamsplitter to erase the frequency difference between the two photons undergoing Bell state measurements. I'm even more interested in some of the bullet points listed here. For example, develop networking protocols extended to higher dimension frequency band entangled state. Also, using hyperentanglement to boost the success rate for Bell state measurements. For example, a few years ago, ORNL had one using time polarization hyperentanglement for superdense coding. Can frequency play such a role as well? Finally, most of our current work is still limited to single photons or at most a photon pair. It will be very crucial for any real-world applications to extend to multiple photon pairs and implement, let's say, entanglement swapping between photons from two independent sources. Okay, this is the end of my talk. I would like to thank the support from my lab colleagues and of course the mentoring from Prof. Weiner. I also want to thank my best colleagues in ORNL, always making sure I'm not alone by myself in so many visits over the years. Thank you.